Welcome to the deep dive. Today we're unlocking something really interesting from the online encyclopedia of integer sequences, the OEIS.
Ah, yes, a fantastic resource.
We're focusing on one specific entry, A000332. Our mission really is just to explore this sequence and see where it leads us.
And A000332, it's elegantly defined. It's the binomial, coefficient binomial n4.
Right.
Mathematically, that's n1, n2, n3, all of that divided by 24.
So in simpler terms, it's counting how many ways you can pick, say, 4 distinct things out of a bigger group of n.
Exactly that, the number of possible combinations.
Okay. And the sequence itself, if you look it up, it starts kind of slow. 0, 0, 0, error.
You need at least 4 items to choose 4 from.
Right, makes sense. Then it kicks off 1, 5, 15, 35, 70.
It grows pretty fast.
It really does. What's captivating, I think, is how this seemingly simple formula, it just shows up in all sorts of places. Geometry, abstract algebra.
It's surprisingly versatile.
Okay, so let's jump into maybe the most visual example first. Yeah. Geometry. A000332 actually gives you the number of intersection points formed by the diagonals inside a convex n-gon.
Right, with the small caveat that no more than 2 diagonals cross at the exact same spot inside. A sort of general position assumption.
Gotcha. But it's incredibly visual, isn't it? You draw a polygon, draw the diagonals.
And you count the crossings inside. What's fascinating is how it quantifies the internal complexity.
Yeah.
You add just one more side, one more vertex to your polygon,
yeah,
and you can literally see the number of these interior crossings jump up following this sequence. It makes the formula feel quite concrete.
That's a really neat picture. Okay, shifting gears slightly, but staying with geometry. A000332 also counts the number of equilateral triangles you can find inside a bigger equilateral grid of points, say an array with n rows of dots forming a big triangle.
Oh, right, regardless of orientation, so upwards pointing, downwards pointing.
Exactly, all of them. You imagine this big triangle made of like little points? This sequence tells you how many smaller equilateral triangles you can actually draw using those points as vertices.
And this idea, this counting of geometric shapes, it doesn't stop in 2D or even 3D.
No. Where does it go?
It extends into higher dimensions. A000332 is what's called a figurate number for the regular 4 simplex.
The pentateuch, right.
The pentateuch, exactly. It's the 4-dimensional version of a tetrahedron.
Wow. So just like tetrahedral numbers stack up triangles in 3D, this sequence relates to stacking tetrahedra in 4D.
In a sense, yes.
Mm-hmm.
It helps us understand the structure, the combinatorial count within these higher dimensional objects. It's fundamental to that kind of hypergeometry.
That's pretty amazing. It describes these complex shapes. Does it connect to maybe more down-to-earth combinatorial problems?
It does, actually. Think about binary strings, strings of zeros and ones.
Okay.
A 000332 counts the number of ways you can arrange 4 ones in a binary string so that no 2 ones are next to each other. They all have to be separated by at least 1 0.
Oh, interesting. So like for a 5, ket of 5? Wait, how does that work?
All right, so for A5, which equals 5, you're actually looking at placing 4 ones in a string of like n plus 3, so 8 characters here. And there are exactly 5 ways to place those 4 ones with zeros in between. So none of the ones are adjacent. Like a 10 to an 010 is one way.
Ah, I see. That's quite practical. You could use that in coding or pattern analysis.
Definitely. And moving towards the more abstract end, AN, also pops up as the number of independent components of something called an antisymmetric tensor, specifically rank 4 in n dimensions.
Okay, antisymmetric tensor, rank 4? That sounds pretty dense. What does that mean in practice?
It does sound intimidating. Think of it like this. In physics or engineering, you sometimes deal with quantities where the order of things matters, but in a very specific way, swapping any 2 indices flips the sign.
Okay.
An antisymmetric tensor captures this. Rank 4 means it relates 4 directions or indices. AN tells you how many fundamentally different measurements or components you need to fully describe such a system and in dimensions without redundancy.
So for A5, in 5 dimensions, there are only 5 unique pieces to this rank 4 antisymmetric thing. Like, say, component A1234 is one, A1235 is another.
Precisely. Those 5 components capture all the unique information. The sequence gives you that fundamental count. It's foundational in fields dealing with multidimensional interactions.
Incredible range. So looking at the math itself, you pointed out something really striking earlier about prime numbers.
Ah, yes. The fact that 5 is the only prime number in the entire sequence, A000332.
Why is that? It seems unlikely.
It stems directly from the formula, n, n1, n2, n, 324. You're multiplying 4 consecutive integers.
Right.
Now, any set of 4 consecutive integers is guaranteed to contain a multiple of 4, another multiple of 2, so divisible by 8 total, and at least one multiple of 3. So the product n1, n2, n2, 3 is always divisible by 8, 3, up to at least 24, as long as n is 4 or more.
Okay, so the division by 24 always yields an integer.
Always an integer. But more than that, as n gets bigger, those 4 consecutive numbers will contain more and more factors. It becomes almost impossible for the result not to have multiple factors. The only time it slips through and gives a prime is right at the beginning, when n5.
Let's see, 5 times 4 times 3 times 2 is 120. Divided by 24 is 5.
Exactly. 5, after that, the terms grow rapidly and are always composite. 15, 35, 70, none are prime.
That's a neat property. And there's another connection too, right? Something about building on other sequences.
Yes, this is quite elegant. If you ignore the initial zeros, A000332 is exactly the sequence you get if you take the partial sums of the tetrahedral numbers.
The tetrahedral numbers, that's A000292 in the OEIS, which go 1, 4, 10, 20.
That's the one. So the first tetrahedral number is 1. The first term of A000322, ignoring zeros, is 1.
Okay.
The sum of the first 2 tetrahedral numbers, 1 plus 4, is 5. That's the second term of A000332.
And 1 plus 4 plus 10 is 15.
Which is the third term. And 1 plus 4 plus 10 plus 20 is 35, the fourth term. It matches perfectly.
So A000332 isn't just related to the tetrahedral numbers. It's literally built by summing them up.
Precisely. It shows this beautiful hierarchy in sequences, how simpler ones can build up more complex ones. It's not just a coincidence. It reflects a deep structural relationship.
Wow. Okay, so from counting points inside polygons to triangles and grids, components of tensors, patterns and binary strings, even being built from tetrahedral numbers. This sequence, A000332, it really packs a punch for just being binomial N4.
It really does. This dive into A000332 is a great reminder, I think, that even these fundamental mathematical building blocks hold keys to understanding really complex structures across so many different fields: geometry, combinatorics, abstract algebra.
The connections are just waiting there.
They often are, yes. Once you start looking.
It makes you wonder, doesn't it? We encourage you to maybe visualize some of these connections yourself. Think about how many other seemingly simple sequences in the OEIS might be hiding this kind of rich interdisciplinary story. What other basic formulas might be quietly shaping structures we see all around us?